Our final talk of the afternoon before we have a break and then go into our breakout sessions will be given by Jose Hurtado, my co-chair, who will be discussing EVA operations and implications for modern in-situ field data.
Thanks, Tim. And I want to thank all the other speakers in this session. It's been really great. I'm going to stop my video here just to preserve some bandwidth. All right, so to begin, I'd like to acknowledge Matthew Miller, who wasn't able to join us at today's meeting, and he asked me to fill in with some thoughts on the intersection of EVA operations and the acquisition of in-situ data with field tools and instruments, all the sorts of things we've been talking about today. Next slide, please. The main message we'd like to get across is summarized here, and it's the question of how in-situ field science instruments fit into the broader EVA workflow. There's been a lot of work in this area. It's been done by numerous groups, including NASA internal efforts, survey-funded efforts. And the questions they've gone after are the use of field instruments to collect science data, the collection of associated metadata, assessment of how that data is used to enable meaningful science. And one of the take-home messages from the EVA operations perspective is that the results of these efforts need to be clearly articulated so that they can be successfully enabled in a flight context. Next slide. Now, I'll point out as examples that there's two of these efforts, Basalt and Desert Rats, that I'm showing here. They've published a variety of papers on various aspects of this kind of work. And so as we progress towards Artemis and the next generation of lunar and planetary exploration with humans, more of this output and documentation will be important. Next slide, please. So among the common threads in thinking about EVA operations in science is that opportunities for meaningful insertion of science and field instruments and tools specifically is that they must respect the broader hierarchy of mission constraints, as you can see in this diagram here. These constraints include everything from mission objectives and resources that are available, safety considerations, operational constraints, as well as the EVA plan itself. Next slide. On the other side of the coin is how the science discovery process works. And that process is illustrated in this diagram. At least for field geologic work, it involves iterative and flexible planning and execution. So science needs to respect mission constraints, and the associated tools and instruments of doing that science must enable this iterative process. Next slide. So these diagrams, these are from some of those papers that were published from the results of Desert Rat and Basalt. These are illustrative of how previous studies have explored integration of in-situ data with mission operations from the standpoint of real-time data acquisition and the communication of that data and sort of real-time decision-making during EVAs. And that is all really important stuff. But what might be missing is also understanding of how mission operations can facilitate in-situ data capture and utilization to do science in the long term. So this is a big point that Matthew Miller wanted me to sort of get across. And in the next slide is a summary chart that Matthew put together that illustrates some of these issues. So data acquisition with field tools and instruments and processing of that data will obviously occur over various timescales. There's those timescales that occur on the order of days to weeks, which shown on the left here. And then there's those things that occur over longer timescales, months to even years, even decades. The more real-time part of this on the left is focused on collecting data and working with instruments and tools in a way that is immediately actionable, at least ideally, in terms of decisions and answers to questions that an astronaut operator might have during an EVA. This is the part that a lot of focus has been put on by a lot of different analog activities. On the right is the part that involves taking that data and doing the curatorial, archival, and analysis work that will enable detailed science. And so how we do all this in a terrestrial setting, including the analog studies that have been done, needs to be mapped to the mission constraints and processes of spaceflight. Next slide, please. So in light of this, it's worth thinking about what field instruments and tools, what they should be doing for us. They should augment and assist. That's what tools do. And they must do that without becoming themselves hindrances. So how to enable these functions in an optimal way for astronauts on an EVA is an active area of research, and we've heard a lot about that kind of work today. Next slide. And there's lots of instruments that exist today to provide the data to do those sorts of things for us. And again, some of which we've heard about today, and we'll be discussing them more in the breakout sessions. It's important to realize that each one of these has its own technical capabilities, value proposition, own limitations, and overhead, all those sorts of things. Next slide. And so when we assess the utility of these tools, it's important to reflect on the types of decision making that they can enable, in light of their capabilities and things like overhead. And the kind of decision making that they can enable both in the real-time context, so those are questions like, where am I? What's my location, or what's the location of what I'm studying? Identification of materials, outcrops, sensing in general, all these operationally and science operationally focused questions that require actionable answers at short timescales. But as I mentioned earlier, I want to sort of emphasize that the data, the metadata, and the context that go with it for long-term science shouldn't be forgotten in all this. Next slide. So in general, what can in-situ data provide? So if you map the instruments I mentioned earlier to capabilities, you see it gives you wide access to data for spatial and compositional context, for measurement of environmental parameters, surveying, determination of physical properties, all those sorts of things. Some of these can give rapid answers to operational questions with a minimum amount of preparation in real time during fieldwork, and hopefully that provides richer situation awareness to the operator and also their mission support team that enables decision making during EVA. Now, most of these kinds of tools and instruments will also provide data to increase the breadth and depth of science awareness and understanding to do science in the long term. But you'll notice I put a lot of asterisks in here. So how rapid is rapid? How much overhead is going to be needed? Are there actually going to be answers that are interpretable given in real time? And how close to real time is that? And in communicating these data to the mission support team, how much of a two-way interaction can we expect to have, if any, in facilitating those sorts of collaborations? So what are the constraints behind all this? Next slide. So each instrument that we are going to think about for Artemis should try to address the workflow expectations and the anticipated mission constraints that it might conflict with, basically all the asterisks that I was just talking about and that are listed here. So these include the time it takes to deploy and use the tool, and the examples that Renee just talked about are really illustrative of this. The time it takes an instrument to yield a result for the user to interpret, and the examples that Deanne was talking about are really illustrative of that too. The difference between an instrument giving a real-time yes or no output versus the detailed view that the science community will want in the long term. So lots of issues here that need to be remembered when designing and implementing the use of in-situ tools and instruments. Next slide, please. So the main message that Matthew and I wanted to convey is that with all these considerations in mind, data integration and interpretation across different users and across a wide range of timescales is going to be a challenge. And I think everybody recognizes that. And it's not going to be just a challenge in the non-trivial real-time use case for instruments and tools, but also the long-term use case. So how can mission operations facilitate in the best way the acquisition of the science data that's going to be needed to really sort of do transformative, decadal survey level science on the surface of the moon. Next slide, and I think this might be my last slide, so I'm going to have lots of time left over to add to the Q&A. So add questions to the chat if you haven't already. As I conclude, here's some thoughts that I offer. For real-time applications, instruments and tools should be optimized for minimum time and minimum user input. Basically make the tool as easy to use and easy to interpret what it tells you as possible. The long-term value of science tools should not be forgotten, though. And there needs to be clear traceability between instruments and science objectives. As Dean mentioned earlier, instruments should really justify their placement on the manifest to get to the moon. And then finally, in any context, tools and instruments cannot replace geologic training and experience. Instead, they are best wielded by well-trained and experienced crews. And with that, I'll I'll wrap it up. Thank you for your attention.